Welcome back and hello to the last video of this course. In this last video we will now be dealing with a topic which is important for probability theory, in particular for the theory of stochastic processes. In such processes we, for example, have the real line on the x-axis, which is the time, and on the y-axis we have some random state or so. And for all these states we have a value, and that means we have an uncountable collection of random variables. And that requires to define probability measures on product spaces which are uncountable. So a product with an uncountable index set. And the question is if such distributions exist at all. And that's answered by the so-called Kolmogorov-Extension theorem. And you might have guessed that yes, they exist. And let's now see how we can construct such a measure. So let's get started. The topic, so how to construct these measures, that's projective limits, and we will of course define them. Just as I mentioned in the introduction, what's the problem actually we are going to solve today? One example from basic probability theory. You have an experiment, for example, a countable number of coin tosses. Okay, that's not uncountable, of course, but that's infinite. So there are infinite coin tosses. And one question is, can we, for example, define the joint distribution of all these? And up to now we cannot. Because we only dealt with finite products in this section until now. But here I would already need something quite sophisticated from measure theory, which is an uncountable but infinite product measure for this joint distribution. And it's even worse if the index set is here really an interval. Then we would have a product measure, a product on the on an uncountable product with an uncountable product index set. Yeah. So we need to construct probability measures on uncountably infinite product spaces. And how are we going to do this? As usual, using outer measures. And what we also need here, again, the projection operator. So J is a bigger set, so that's here a product space with a larger index set, so more coordinates, and here you have fewer coordinates, and you just leave out the rest, and that's here the projection. We need this. On the next slide. The topic are projective limits, and let's define them. Projective limits are based on projective families. A projective family, so that's this here, only require finite products because recall J subset of I, and the index F here means J is subset of I and J is finite. And what this projective family does is it has all these PJs here. I something maybe uncountable, but PJs, these are all only for finite subsets of I. They are defined on this finite product sigma algebra. And that family is called projective if the following holds. Okay, you can project all coordinates from I to J. You can further project them down to H. And the family is called projective if it doesn't matter if you first project down to J and then to H, or immediately to H. Yeah, that's then a projective family. So what's then a projective limit? So here I only have measures on the finite product spaces, and the limit should be a measure on this uncountable index set. uncountable product. Well, and Pi is a projective limit of the family Pj if, well, take all coordinates, project down to j, and you obtain j for all possible j's, then we say that Pi is the projective limit of this family of Pj's, j finite. And as usual with limits, they should be somewhat unique. And that's the first remark here. Projective limits are unique. Projective limit here is a measure. Pi is a measure. When is a measure unique? And we had a result. I don't remember the number. You could look this up. But it said that if you have an intersection stable generator of the sigma algebra where two measures live and they agree on this generator, then they agreed on the whole sigma algebra. So in order to show uniqueness here, let's assume we have two projective limits. We only have to show that they are the same on an intersection stable generator. And this here, the H prime here, is a intersection stable generator. So what are you doing here? J is a finite subset of I. You take for a finite index set some AIs in Fi, and for all the rest you take the whole space. Well, but on such sets, Pi, what does Pi do? Pi is defined because of the property here, Pi projected down here to j equals Pj. So for such a set here, A is such a set, Pi of A equals Pj of the interesting part here of the set A. And if you have two of them, they would both be the same because Pj's, they are given through the projective family. They would be the same on this generator, so they are the same. So we have shown that projective limits are unique. The interesting bit is if they exist. And that's Kolmogov's result. And I walk you briefly through the proof here. So H prime as above, and that's a semi-ring. We had that in the last video, I think. Again, I take an A of this form here. And, well, on H prime, I can define mu of A. If mu is then a set system, a function on H prime. Mu is a function on H prime. Properly defined here. And we had these theorems here, 2.10 and 2.16. And the question is, I have defined mu here on H prime. How can I extend mu to the sigma algebra generated by H prime? And that was, in the first part of the whole lecture, a main topic. And what we are doing here, let's jump to 2.10 and 2.16. 2.16, we had a semi-ring. We had a set function on the semi-ring, which is sigma finite and sigma additive. Then this theorem guarantees us that we can extend this mu here uniquely to sigma of H. So to the sigma algebra generated by H. And that's exactly what we want here. So we have to check if we have all necessary things for our mu. Sigma finite, that's okay because we have here probability measures. All p's were probability measures, so they're also sigma finite. The interesting part is sigma additive. So this mu here, is it sigma additive? That's the question. And for this, we had theorem 2.10. It concludes something is sigma additive. What does it need? We have a semi-ring, we have this. Mu is finite, that's true because of the probability measure. Finitely additive, that's true because that's just defined on this semi-ring, and we can easily show finite additivity because the things on the right hand side there are finitely additive. And inner K regular, and K is a compact system, then it's sigma additive. So we need to see that the mu we defined here is inner regular with respect to a compact system. And the compact system we're using is this here. You will show in one exercise why that's a compact system at all. So what is it? You take an interesting bit and a not so interesting bit here. So in the interesting bit, you take only compact sets. You take a compact set in every coordinate in J and the full space in all the rest. That's a compact system, and that's part of H because H prime, I think. Because, well, compact systems are measurable, so that's part of H prime. Yeah. And as we saw, we have to show that mu is inner regular with respect to K. That's the deal. So why is mu inner regular with respect to K? Inner regularity means we pick an epsilon and some A in H prime. So A was this here. We have to see if we find a K in this system here, such that mu of, so K is part of A, so subset of A, and the difference, mu of A without K, has a measure less than epsilon. And that's what we have to see. So we have to see if we find K, which is of this form, such that mu of this set without this set being a subset of the set A, is less than epsilon. Okay, it's J times epsilon, but J is a finite number and it's fixed in all the calculation. So I could also have used a different epsilon here and go through the calculation again in order to have an epsilon here, but I don't do this now. So how can we conclude this? There's one thing we need. And I forgot to say, omega has to be Polish. It has to be Polish because it has to be Polish also here, I think. I just didn't write it down. No, here it is. On Polish spaces, we had one result which says that every measure is inner regular with respect to the compact sets on the space. Which means that in a Polish space, we find a Kj, subset of Aj, such that the difference is less than epsilon under Pj. That here comes from one result we had, and the Polish property of our measures. And that's already pretty close. We want something, so we have something small epsilon, and you want something also smaller than, well, factor times epsilon. But we can just pick them and use them in order to construct this set here, which is in this compact system K, apparently. And we can measure mu of the set A minus the set K. Well, and on such a product, okay, there's all these non-interesting coordinates. We can also put them down below. And mu of something times the full set for the rest, that's just pj of the difference by definition. And here we have a product without the other product. So this product here without the other product. So this here without this here gives me all of this here. Oops. Let's do it in a different color. So all this here we have to see. So what's that? That's smaller than this here, I claim. Yeah, for every coordinate, pick aj without kj. So what's that? In the a1 direction, we have this here without this here without this here. Yeah, this without this, which is like this here. And we have the set, well, which is this whole set. This without this on the first coordinate. On the second coordinate we have, well, this here from here to here without this, so it stays like this here. Okay, the drawing is not the very best, but when you do all the drawing, then you see that in such a product space, this here, so product minus product is a subset of the union over all coordinates of all these here. And for all these here, I can again use the projective property. P of a union is less than or less or equal than a sum, like this here. And here I have again the projective property. We can exchange this by pj of aj minus kj. And we have that this here is at most epsilon. And that's the reason we have here number of coordinates times epsilon. So that's small, which eventually now shows inner regularity of mu with respect to the compact system K. And that's it. We have shown existence of a projective limit. And that's essentially it for this whole lecture. There will be a next course, and the next course is then on probability theory based on this measure theory concepts we now had. Hope to see you then. Bye.